Hello everyone, welcome to pipeeng.com. Today I'm glad to introduce you another tool we developed for analyzing Vortex in induced vibrations. So for pipeline exposed rivers, that's pretty common integrity issues. Mainly because of the constant water erosion, the water channel relocation. So the pipelines, especially those aged ones, it's very common for them to gradually expose in the river stream, either seasonally or constantly. When we analyze the real risk of the pipeline at exposed rivers, so very common that the pipeline operators needs to prioritize the locations to do the repair because you might find hundreds of exposed pipe locations for your pipelines, but you only have a limited budget for a certain given year. So it's paramount to to really run the pipe stress analysis and really do this as vortex induced vibrations to see if your pipe is really at high risk or your pipeline has a little bit more time for their lifespan. So this is quick tool is really developed based on the analysis and assessment of unsupported subsea pipeline span published by United States Department of the Interior Minerals Management Service. So this is a pretty common way of analyze the vortex-induced vibrations. So let's dive into the tool itself. Again, like all our other tools, we offer imperial units and metric units, depends on where your project's at. For this tutorial video, I'm gonna just use the imperial unit. Um, the first part is the pipe data inputs. We have the kind of same drop down for many of our other tools. Basically, if you have a pipeline that is at standard size or wall thickness, you could just quickly choose from here. For those pipelines that has a different wall thickness or size specified here, you can go through custom and to open a window for you to manually put in, let's say for this case, we're going to use, let's say 10-inch pipe, wall thickness, we can go for, like say, quarter-inch. Then this is for the concrete coating thickness. For a lot of pipelines at the river crossings, we use concrete coating around the pipeline to provide more buoyancy control measurements for it to lower to the water. So if you have this coating thickness, if you know it, put it in. If you don't have it, you can put it 0. And the density content in the pipeline is really what the fluid the pipeline is carrying. So if you're carrying water, oil, if you know density, put that in. If you use gas, natural gas, you could put in 0.1, for example, just to simulate a very low density. And then there is some typical inputs here. Density of a water body, 64. It's kind of generic typical value we use. You could tick the box in front of it to manually change it if you want to. Same thing for density of steel. You could change it if you have a more precise number. Density of a concrete with coating. That's the concrete, the thickness. The same thing for the modulus of elasticity of the pipeline. Some people prefer to use 30 instead of 29. For free span fixity index, so this is like an embedded in factor to simulate a different pipe restraint scenario. So the value of 1.5, it's for the open end. It's simply the unrestrained fully fixed end, and 3.5 is a fixed end. It's kind of like two anchor points on both of the exposed pipe across the river. But we all know in a real case it's kind of like in between because soil and pipe is not a technically an anchor point. It's there's a pipe soil interaction we have to consider. Even really consider is a virtual anchor has quite a bit of distance. Because the virtual anchor defined as the pipe soil friction is big enough to act as a anchor point to offset any of the thermal expansion, all that stuff. So you could use value between 1.5 to 3.5, depends on how what the conditions of the site. But generally, if you're not sure, I think 2.5 in the middle is a pretty good approximation. And then for straw hole number, this is a constant. And then we're going to generate this graphs basically with the axes to show different velocity of the river, basically the river stream applied to the exposed pipe, and this is the maximum allowable span. So obviously, the higher velocity is we will see more lateral force applied, more lateral force and vibration applied to the pipe, and then so you have a less maximal allowable span. And we really have this table below for everyone to manually put it in the range. For example, if the river can be 1 foot per second, to you can put in any intervals you feel like for your project. All depends on the hydrology study of the river itself to see the range. Because we know for the high water season, low water season, the velocity could be vastly different for the river. So this is really just to get a study so you can have a sense at what velocity would be your maximum span, then you can have a better understanding of your pipeline risk. So this gonna give you pretty nice graphs to put in your report and do your analysis to prioritize your mitigation for your pipelines at the rivers. I want to also mention that this tool also offers the same features like all our subscribed tools. You could choose to save it. You could choose to save it in a cloud server. It's going to generate a file for you to revisit. Or you can download it to your local drive. Then you could retrieve this local drive by using the open file features. And then you could generate a PDF report, which you could include in a file it for your project folder. So that's everything about this a Vortex induced vibration tool. If you have any questions, feel free to reach out to us. Thank you very much.